So, we're going to talk about some wireless sniffing and some Kismet stuff and whatnot. So, wireless sniffing's been around since the late 90s. Packet sniffing in general has been around much longer, but it's still something we need to worry about now. You'd think it would have gotten a lot easier. It's gotten slightly easier. It's still sort of a pain. We really care about it now, though, because more and more of the last mile to the user is wireless. It's either wireless in the home, where they get one Ethernet connection from their cable modem to their router, and then everything else is over Wi-Fi. Or in the offices, they do, instead of running cables to all the desks, they do Wi-Fi deploys or similar. We've got more and more sensors, IoT stuff, industrial sensors, air conditioning, things like that are now connecting over Wi-Fi or other RF. And bring your own device for offices are huge. I don't know how many people deal with that for IT infrastructure, but everybody wants to bring their phone to work and have it on the Wi-Fi instead of their data plan and check their email at work. And now all of a sudden we've got all these other devices that are unmanaged, that we can't control, that are connected to the networks that we have to deal with. And oh boy, Wi-Fi, plenty of security problems. We've always enjoyed that, and we still seem to. Just get rid of the Ethernet. We don't need it. So the Kismet project, it's a little over 18 years old now. I used to joke a couple years ago that it was, it's 10 years old, or my software is old enough to drive. Now it's old enough to buy cigarettes and vote. So it's undergone at least 2 major rewrites over that time. That's replaced most of the code. The latest one is happening now, more or less. The last few years adds all new capabilities, a new user interface, new logging, all sorts of cool stuff that I will be happy to show off. Why do we need another tool just for Wi-Fi? There's a whole bunch of other tools that monitor packets. You've probably heard of 1 or 2 of them. I heard there's some conference about this other one. I don't know. But the problem is Wi-Fi is sort of a unicorn. It is shared medium, and it is even more of a shared medium than like hubbed Ethernet is, because it's not only your network that's impacting you, it's every network in your area. So everywhere the signal reaches, it impacts your network. The amount of bandwidth you have available for your network can be impacted by the office or the apartment next door to you. If they're doing a lot of traffic on the same channel as you are, you're going to have performance problems that are nothing to do with any of your equipment. Remember the OSI model? You're suddenly going to really care about layer 1 and 2 in ways you've never had to care about them before, once you get into Wi-Fi and RF. There's lots of ways to detect that a network is present, but knowing that a network is present doesn't mean you know what's going on with it. So you need to be able to see what's actually happening at the packet level, or even at the RF level, to figure out what's happening to your network because of it. Here we have the Wi-Fi unicorn. There's several ways you can discover that a network is present, but what we really need to see is the packets. So you can, look at the scanning mode, which is what the operating system uses to populate the list of Wi-Fi networks you can connect to. Tools like NetStumbler use it, Insider, some other tools use that. It'll tell you that a network is there that is advertising that it exists, but it won't tell you how many clients are on it, how much data is going through it, what's going on, and it won't tell you networks that have hidden network names. Some enterprise APs can do access point assisted versions of this, where it'll either tell you, all the clients that are connected to its network. Some enterprise networks will even advertise, I'm a network and I have 14 clients connected to me. It just puts that in the advertisement. Again, it tells you a little bit about what's going on, but it doesn't actually let you see the packets. And we're at SharkFest, we want to see the packets. That's what we care about. So you can just, I don't know if any of you have tried, you can just open your Wi-Fi interface in Wireshark, and it will start doing something. What it will give you is a bunch of lies. If you just open the interface, you'll see, notice here where it says Ethernet 2. You're getting what the operating system thinks are Ethernet packets, not your Wi-Fi packets. So Wi-Fi tells the operating system, I'm an Ethernet card, because everything understands Ethernet cards. They understand Ethernet frames. They can handle data that way. The data packets on Wi-Fi basically look like Ethernet. They have the snap header. They have the standard IP headers and whatnot in them. So it makes sense that it presents it to the operating system that way. But you'll only see the data packets on the network, not the actual Wi-Fi packets. And then what data packets you see also really depends on the type of network and the drivers and the operating system. So typically you'll see data packets from you and to you from the device you're running it on. You might see broadcasts, you might not. You probably won't see anyone else's packets. So you've got a very limited view that doesn't really tell you what's going on. So if you're actually able to capture the Wi-Fi packets, you'll notice that it'll tell you radio tap header, so that's signaling headers that are device specific, and then you'll actually get the IEEE 802.11 packets in your capture. So that's what you want, but it's difficult to get there. So for wired Ethernet, there's promiscuous mode, and it just turns off the MAC address filtering and gives you everything it sees. Switch networks present a little bit of a problem, but after that, it's no big deal. For wireless, it's a completely different mode that it has to put the card in. The card operates completely differently. So it's called monitor mode, and it generates the raw 802.11 packets for you to sniff. The operating system doesn't understand 802.11. You'll see wacky stuff where it doesn't really know the MAC address of the interface anymore, but Wireshark captures it fine, and that's what you care about. Monitor mode isn't part of the spec. Lots of drivers support it. They all support it a little differently. There's no standard. You don't pass Wi-Fi certification by having monitor mode. So getting it to work is a bit of a problem. So the fun part. We need an operating system that supports monitor mode. In general, OS X and Windows don't, with a few exceptions. We need a Wi-Fi card with firmware that supports monitor mode. Some manufacturers, to make the firmware smaller, especially on things like mobile devices, so things like Raspberry Pi and phones, they strip the capability to do packet capture out of the firmware of the card. So there isn't even a way to kick it into this mode. You need drivers that support monitor mode correctly. So even if you have a card, like the Intel card and firmware can do monitor mode in Linux, in Windows the driver doesn't support monitor mode, so you can't actually get the packets then. That's a lot of different things that need to all work together. So what it means when you're looking for Wi-Fi cards to buy, the specific chipset matters. Manufacturers love to buy the cheapest thing and put the same label on it. So you can get 3 cards that are the same, like Netgear 1400 or whatever, and have 3 completely different pieces of silicon in them, some of which support monitor, some of which don't even work in Linux or whatever. So we'll dig more into that in a little bit. So I said monitor mode isn't really a defined mode. There's no standard for it. There's no specification for what you return, how it's formatted, etc. So it requires reverse engineering the firmware for the driver authors to figure out how to do it if the developer didn't document it. Even when it does work, there's a lot of variance in how well it works. So the common failure modes is, you'll get advertisements for the network being there, but you won't get data. Or you'll get no packets at all. Or you'll get weird mangled packets that are completely invalid mixed in with your valid packets. It's a lot better than it was 10 years ago, but it's still kind of a mess. So Kismet tries to automate solving the edge cases of that as much as possible. There's some other tools that will also do it. Wireshark and PCAP can do some monitor mode enabling if the drivers use the standard methods of doing it. With bogus packets. So there's a checksum in the Wi-Fi standard that's supposed to indicate that the packet is valid. It's called the frame checksum or FCS. You'd think this would solve the problem. You check the FCS, you're good. Some drivers, like the Atheros 11AC drivers in Linux, have a checksum flag. They say it's valid. It's not. I went digging into it. They seem to calculate the checksum based on whatever's in the buffer instead of what the checksum was when they received it. So every packet has a valid checksum, no matter if it's complete garbage. Some drivers just don't report checksums at all. You get valid packets, you get invalid packets, and it's just a mess. So if you're trying to figure out how many devices are near you, you might have 50 real ones and 500 fake ones because it's corrupting the MAC addresses in the air. So then when it comes to actually sniffing the RF protocols, so traditional Wi-Fi, like the old school 11B, 11G, and 11A stuff, they used a much simpler radio encoding. So it was, 11B was really simple and really slow. So, it's loud, it's slow, it's easy to hear what it's yelling. G and A got a little bit quicker, but they were still used, pretty basic radio encoding methods. So it had one transmitting antenna. So even if you had an AP with 2 antennas, one was for receive, or 2 were for receive and 1 was for transmit. So it was, simple, 1 antenna talking. If you're in range, you're probably going to see all the packets from these networks. Now we have MIMO. Who's had fun with MIMO yet? Few people. So MIMO is a thing they added in 11N and 11AC, and it's going to be even more so in 11AX and the newer protocols. So it stands for multiple in, multiple out. And what that really means is before you had 2 antennas that could see packets and 1 antenna that could transmit them. Now you could have 3 antennas seeing packets and 3 antennas transmitting simultaneously. And they do all these wacky RF tricks so that each antenna transmits slightly differently than the one next to it. And sort of it effectively doesn't quite triple, but it greatly increases your ability to send multiple pieces of data simultaneously and to reconstruct fragments of data because you can see multiple images of it at once. So you get great bandwidth, and it's sort of it's part of what makes 11N and 11AC so much faster now. But it also means that now a laptop here, instead of an access point transmitting and the packet hitting the laptop and the packet hitting the sniffer, now the AP transmits, the packets bounce off the walls and whatnot, and chunks of them hit the laptop. And because of MIMO, it can reassemble that and make a packet out of it. Different chunks hit the sniffer over there because it reflected off the wall a little differently. It doesn't see the packet. But since the packet arrived correctly at the client, it's not going to get retransmitted. So now all of a sudden you have your physical location matters about whether or not you'll be able to see data. So sniffing the new stuff is much harder, and we'll cover more of that. It's definitely a challenge now to sniff the higher speed. Then there's the new stuff they've added in 11N and especially AC, which is beamforming and phased array antennas. So this is next level sci-fi stuff, where they have 3 antennas in a row that all send out a signal to all directions. And by tuning the time of them by nanoseconds, they can make that signal act as if it were beamed at a specific point. So now not only do you have to be in the right location to get all the components of the signal coming from all the antennas, but the access point is deliberately optimizing it so that it's aimed that way. And if you're over here, you might not see it at all. So that's great for Wi-Fi. It's terrible for sniffing networks. It's terrible for monitoring. So it's just another problem that we're going to face as that becomes more and more prevalent. And that becomes increasingly so in 11AX and the newer standards. And the problem with the newer protocols is you need a new card. You'll see parts of the protocol because they use backwards compatibility. So you might see that a network is advertised that it exists, but you won't see any of the data or any of the users on it if you have an older card. Unfortunately, new cards cost more because they're new. Fewer companies make them, so you don't have as many options, and they're not commoditized to be, $10 cards anymore. There were probably 50 different brands of 11G cards that worked for monitor mode. There were maybe about 10 that work well in 11N. I can think of about 4 that work for 11AC and 1 that works for 11AX. And it only works if you use an unreleased Linux kernel. So what do we actually have available for capturing with? It depends on your operating system. So with OS X, shockingly, the built-in card from Apple is the one that works. I wouldn't have expected this. They don't like to share. They don't like to play nice with other people. I'm amazed that that's the one that works, and it works really well. So if you're looking to sniff 11N or 11AC, a MacBook can do it quite well. As far as publicly available open source code, there's nothing else I'm aware of on Mac that can do monitor mode. None of the USB cards have drivers that can do it, and there's no API in the operating system to enable it. In theory, it's possible to do some with USB cards, but it would require a bunch of code that hasn't been written yet. But stay tuned, we might get there. Windows. There is the ERP cap from Case, but as they said yesterday, here are the last ones we have. So it's sort of end of life. The drivers are unmaintained at this point. There are some commercial products. I believe OmniPeak and a couple others, they distribute their own hardware and drivers. They are very, very expensive, but if you need them, you can get it that way. In theory, again, USB is capable or possible, but there's no code to do it yet. There is the Windows Linux layer, WSL, on Windows 10. It cannot do USB. WSL2 is in early alpha mode now. It just released to the Insiders channel yesterday. I believe it's built on Hyper-V, so it will not do USB either, unfortunately. So there aren't too many great options on Windows that aren't commercial. In Linux, it's your best chance of making it work. There's a whole bunch of different chipsets out there, different companies that will work with monitor mode. Intel that comes built into a lot of laptops now works pretty well. If you have a modern kernel, it works quite well. Most Atheros cards work. They're pretty common. The Raspberry Pi can be made to work, and there's a bunch of other things. There's small embedded Linux systems that can be very good for feeding packets to another system. So you can capture packets on that and then open them in Wireshark on a full-fledged system, and I'll have some examples of that later on. You can also usually run Linux as a live CD or a live USB, where you can just dual boot your laptop into Linux without touching your hard drive, and that's a good way to get capture mode. So there's multiple distributions of Linux that are meant to run live off a USB, if people aren't familiar with them. Kali is the most common. Pen2 has a lot of support as well. There's a new one called Parrot. I'll be honest, someone asked me about Parrot this week, and I said all I know about it is that it often breaks in weird ways and nobody knows why. I then tried to build packages for it, and it broke in weird ways, and I don't know why. But if you're not really a Linux person, if you're not looking to run Linux full-time, a live CD is a good way to get going. It does often require, if you're on a Windows laptop, that you disable secure boot, because it won't let you boot off a USB otherwise, but it's a good way to boot off a USB drive, do some stuff in Linux, reboot back into Windows, and you won't have messed up your hard drive or had to deal with configuring things. There's virtual machines. Everybody wants to run Wi-Fi capture in virtual machines because they don't want to boot Linux. There are a lot of nasty edge cases that make them not work, unfortunately. The only things that will work in a virtual machine, if it works at all, is going to be a USB device, because you can't use their built-in NIC because there's just no way to virtualize it down into the VM. I've personally had acceptable luck with VMware on Windows. So VMware Workstation can do USB pass-through with a Windows host. However, I've heard of lots of other people who've had worse luck with it, and VMware on OS X does not appear to work well at all. Hyper-V can't do USB. VirtualBox can, but I've had it generally not work. So if you're looking for pain and you're looking to fight with it, you can probably get it to work on some systems. But if you're looking to just have something that functions, it's probably better to boot off a live CD or a live USB. Hyper-V on Windows cannot do USB. They have a file system pass-through for USB flash drives, and that's it. You can't connect any other type of USB through to it. Often the community people will get very angry at you if you say you're using a VM. The Pen2 guy in particular says, if you're running a VM, I will not talk to you. So it's a little bit limiting. I said USB is the only thing that will work. It may be possible to do PCI pass-through if you're on Linux. If you're already to the point that you're running a VM doing PCI pass-through, then you don't need this info. So the one other option then is remote capture. So Kismet now supports remote capture over TCP. So you can take any cheap Linux system and use it to capture packets locally and then funnel them to a full Kismet server running on Windows or WSL or OS X or another Linux system or whatever. So any device that can capture packets to any system capable of running the Kismet server code, you can do transparent packet forwarding. We'll demo that in a bit. So Raspberry Pis, OpenWrt-based things, and whatnot are good candidates. This little guy is a $15 full Linux OpenWRT router that can run monitor mode, and it plugs into USB. So that's a good option. So when do you not actually need to worry about monitor mode for Wi-Fi? You don't need monitor when you're looking at traffic from, if you're looking at data from a server to your laptop or whatever. If you're looking at broadcast and multicast stuff, if you're looking at data frames and not Wi-Fi. If you can connect to the wired network that your access points are on and monitor from there, and all you care about is data performance, then you don't need monitor. But as soon as you care about seeing non-Wi-Fi packets, if you care about doing Wi-Fi intrusion detection and security stuff, if you care about finding if people have brought access points from home and plugged them into your corporate network, if you care about denial of service and spoofing attacks, if you're trying to figure out why your data performance is crap and you can't see it from the Ethernet side, then it's probably a problem on Wi-Fi, and you're going to need to be able to see the Wi-Fi side of things to figure that out. So Kismet is designed to do basically just a handful of things. It's designed to manage the Wi-Fi cards and deal with all these problems that I just mentioned about all the different drivers. They get configured differently, they have different capabilities, they report packets slightly differently. We just need, it deals with all of that as much as it can automatically. It looks at, it tries to keep the operating system from breaking the config. So the OS will try to come in and, Network Manager will come in and kill your monitor mode interface and reconnect you to the network. Didn't ask it to. And also it'll deal with channel hopping, and we'll talk about channels in just a few. So Kismet is mainly meant to, it looks at the packets and derives from them what devices are out there in the air and how they relate to each other. So it will, Wireshark is packet-centric. You get a list of all the packets. Kismet is more of a, you get a list of all the devices and how many packets each device has sent to whom and whatnot. So you can also generate a packet feed for Wireshark. So you can actually, run Kismet, get monitor mode going, see all your devices, and then shove all the packets right over to Wireshark and look at them. It'll also do more than Wi-Fi, and I'll have some demos of that. So if you've used Kismet before, you're probably used to it looking about like this. Before I get to the next slide, has anyone else seen the new one yet? One person. So, significant rewrite. Kismet now has a web-based UI. You can talk to it over HTTP. It'll give you JSON records back, so you can write scripts against it. It's got a new log format that combines all the logs into one file. You don't have to correlate a half dozen different types anymore. You can feed packets over HTTP. You can do remote capture. It's got all sorts of stuff now. So that's the new interface, which is web-based. If you click on it and see, different network details, it'll break it all down and show you, different things about them. And I'll pull up a live demo later on with more details on that. So you can manage any number of sources simultaneously in it. So in this case, the source that's highlighted right now is running. It's a USB device plugged into the computer, and then all of these are OpenWRT routers doing capture plugged in over Ethernet, passing packets to it.
What version of Kismet is that? Is the new web interface?
It's the latest releases, 2019. The latest one is 2019-04.2. There'll be another one, or 05.2. But if you go to the Kismet website, it's the latest released version. And I have links to packages at the end of the talk. So good news, despite all the rewrites, it's still not blockchain. So why do we have both? Because they do very different things, and you're going to absolutely want to use both of them in conjunction with each other for doing Wi-Fi analysis. I said Wireshark's packet-oriented, Kismet's device-oriented. So traditionally when you're capturing for Wireshark, you plug into the network you're capturing from, or you might need to enable a tap port or a span port. You look at the packets, maybe you need to change VLANs. With Wi-Fi, if you're going to look at just a single user's data, like I said, plug into the wired side. If you need to care about the data flow and not anything about the wireless behavior, plug into the wired side. Otherwise, there's no single place that you can capture all the data about the client that you need to care about. So, for example, what channel is the access point that the user is connected to on? You might not know that. I don't know what channel my Wi-Fi is connected to right here on my phone. Is the problem being caused by user-to-user traffic? If it's one user to another that never leaves the AP, it's not going to bridge into your Ethernet, and you're not going to see it. Is there another access point in the office next to you that's tuned to the same channel that's just hammering the airwaves and contending with you all the time? Or is someone trying to disrupt your network? So what Kismet does is it looks at all the packets and it tries to decode them into devices, like I said. So it'll also track interactions. So when a device joins an AP, it'll create a join record, and you'll be able to see the client connected to it. And you'll be able to see how long the client was on that AP, when it's moved to a different AP, and things like that. It will also let you know if a new network has come up with the same SSID but no encryption. That's probably not a good thing. All sorts of indications like that. It'll derive that from the packet streams. You can include geolocation. So if you have a GPS and you walk around the outside of your building, you can also tag every packet with where you saw it and use that to figure out where problem networks might be located. And you can filter the packets in Kismet by device or by the interface that captured them and then feed that into Wireshark, or you can feed the entire packet stream into Wireshark. So here's how Kismet sees a network, where there's, it'll tell you, so there's not a lot of data on this network and a whole lot of just regular data, regular Wi-Fi packets going on. The general packet counts. And then it'll break down. For example, there's the network that's being advertised. It'll tell you the encryption options. I mentioned some access points will tell you how much traffic they can observe, so Kismet will extract that data and present it to you. So this is an enterprise AP, so it'll actually tell you how busy the channel that it's on is. So Kismet will pull that out and give you some other statistics. And then it'll start telling you all the clients that are connected to it, when they joined the network, when they were last seen on the network, and so on. So Kismet's really based on data over time. It'll decode the beacons, it'll decode all the other types of packets, and extract all that data and present it as easily as it can. And it can also do intrusion detection, both fingerprints and trends, which we'll talk about in a bit. Versus, this is how Wireshark sees that same data stream. So in here you can see, here's an access point talking to a client, here's an access point advertising that it exists. You can get all the data in different ways, and you can drill down into the packets as deep as you need to go, but depending what you're trying to do, seeing the networks like this can be much more useful for figuring out a problem than trying to dig through the packets here. So, Wireshark's packet-oriented. It's all the same info, just presented very differently. And like I said, it's better for digging into the details. So it mentioned, in that capture, there's a bunch of different packet types. So on Ethernet, there's pretty much one packet type. It's got data in it. It's an Ethernet packet. Wi-Fi has 3 main packet types and something like 45 subtypes under them to deal with. But it really breaks down to just the 3 main ones. So management packets define the network. So they like a beacon packet says, here's the network SSID, here's the channel it's on, here's the encryption, here's all the other vendor data that they decided to cram into it. They happen 10 times a second. Without them, a network doesn't exist. Management packets also do things so they control a client wants to join a network or the network wants to kick a client off it. So you can use them to track clients connecting networks, disconnecting, other state changes on the Wi-Fi network. There's control packets. So they're extremely short. They usually have 1 MAC address or 2 in them instead of a standard, source, destination, and transmitter. They're used for collision detection and avoidance. They're used for channel reservation. So a client will say, I'm going to transmit a big packet, and the access point says, you can transmit a big packet, and then it transmits a big packet, and then the access point says, I saw a big packet. It's a very chatty protocol. So you can use this to see, various denial of service attacks. You can see that clients are trying to transmit data and can't allocate the channel time. All sorts of info like that is derived from those. And then finally, there's the data packets where that's what you get if you don't have monitor mode. So it looks like an Ethernet packet on the inside. It's got the IP headers or the SNAP2 headers or whatever. They may be encrypted with WPA. They may be in the clear, depending if the network's open or not. So to really know what's going on, you're going to need all 3. If you can't capture management packets, you can't see that networks are advertising they exist. You can't see if people are joining them. You can't see most denial of service attacks. If you can't see control packets, you can't detect hidden nodes that are in range of your access point, but maybe not in range of your sniffer. And if you can't see data packets, you can't see what's going on. You'll see all of them in Wireshark when you look at PCAP, so that'll give you a bit of a breakdown about what's going on in the network. So we've mentioned channels. Channel hopping. P.T. Barnum, obviously famous for saying, you can see all the channels some of the time, some of the channels all the time. But as Abraham Lincoln said, don't trust every quote you read on the internet. Channels matter. So if you're not familiar with Wi-Fi channels, Wi-Fi breaks it up into different channels. So you might have noticed on your access point you have 1 or 6 or 11 or 52 or something. Sometimes channels overlap, sometimes they don't. There's many reasons that Wi-Fi on 2.4 gig sucks. One of them is that there's only 3 channels there that don't stomp on each other. So Part of why, if you complain about Wi-Fi performance, someone's likely to tell you, go to 11N and get a dual band access point, because the 5 gigahertz channels are much less congested and they don't stomp on each other. So if you're sniffing on 2.4, sniffing on one channel, like if you sniff on channel 6, you'll probably see packets from 3, 4, 5, and all the way up to 9. Depending how close you are to the AP, you might see even more than that. Once you add 11N to 2.4 gig, that gets even more confusing. On 5 gigahertz, there's more non-overlapping channels, but then we have wide channels for 11N, extra wide channels for 11AC, and very, very wide channels for 11AC and AX. So what does this actually break down to? The problem is the radio can tune to a single channel at a time. It's deliberately designed to exclude other channels, because if you're on channel 1 and someone's on channel 6, you want to see as little of them as possible, or your performance will suffer. Typically, you can only tune to one channel mode. So you can be on a traditional channel, like channel 6. Or you could be on an 11N wide channel, so channel 6 plus. So now your radio is listening to 2 channels starting at channel 6. Or 80 megahertz or 160 or whatever. But it means you won't see packets on other modes when you're in wide channel mode. Excuse me. So to see what's happening across all the channels, you need to keep changing the channel quickly. So it's a trade-off. You can see everything that's happening on a single channel, but you won't see anything going on any other channel. So if you have, APs on 10 channels near you, you can look at one of them and see everything that's going on, or you can jump between them and see a little bit of what's going on of all of them, but you're going to miss something. It's like trying to listen to all the radio channels on the FM. You can either be tuned to a channel in your car or station in your car and listening, or you can keep hitting the seek button. And you'll get a little idea of what's going on all the news channels, but you won't hear a full story. So the more channels you have, the less time you have per channel if you want to cover all of them. So, traditional Wi-Fi, B, G, and A. Same channels for 11B and 11G. So 11, some parts of the world, 14, doesn't matter. It's basically the same. You want to cover all the channels. You'll see traffic from 3 channels apart, so you can hop through them, and you'll get pretty good coverage. It wasn't that hard to see all of them. Now we added 0211A. So now there's 38 more channels to worry about. But they don't overlap. So if you noticed before, the channels went 1, 2, 3, 4, 5, 6, just incremental. Now there's gaps between them, 36, 40, 44. They deliberately spaced them out so that they didn't step on each other. So you get better performance, but now you can't see adjacent channels when you're looking at one. So now you need to hop even more. So now we've got 38 channels and the original 11 that we have to hop through. Now we add 802.11n. Oh. So now, because there's 40 megahertz wide channels, and they can be above and below the center channel, now we've got 64 channels we need to hop across instead of 11 to get an idea of what's going on out there. So for example, you could look at channel 1, but also channel 1 HT40, which is the 11N extended mode, or channel 6. But channel 6 also has HT40 above and HT40 below. So now you've got 3 channels instead of 1 to look at there. So, who wants to predict what 11AC is like? Now there's 91 channels at least to look at, depending on your regulatory region. Because now we have 80 megahertz channels. So each of those channels can have an alternate 80 megahertz 11AC super speed channel, plus the 11N 40 megahertz channel above and below, and the original 20 megahertz channel. So we have to keep looking at each of those individually. Then there's 802.11ac Wave 2 and 802.11ax. They've now added 160 megahertz channels. So now you have all of those channels, plus some of those channels set to 160 megahertz wide, plus they've added 80 plus 80 mode, which is 2 80 megahertz channels that aren't touching each other. So now you've got another 8 or 10 combinations to add in. And 802.11ax adds even more. And depending on what you're looking at, there are custom channels that are half or quarter width. So Atheros uses them for some industrial control systems, where it's a normal Wi-Fi channel, but it's a quarter the speed and a quarter as wide. And now you need to also add those in. And since it's only a quarter as wide, there's 4 times as many of them. So we have to change channel quickly to see what's going on. There's two ways to deal with that. You can hop faster, but at some point it doesn't make any sense to go any faster. Kismet goes at five channels a second. Even that, depending how many radios you have or what types they have, can make your system a little cranky. Some radios with crappy drivers really, really don't like changing channel that quickly. And they let you know by causing kernel panics. Or you could add more radios. So it adds more power requirements, that costs more, it's more antennas, and it's physically bigger. But, I mean, you can be pretty subtle. Nobody would notice you walking around. That is Mike Spicer with the Wi-Fi cactus, which I will talk about in a little bit. That is 50 ABGN radios, for the record. So Kismet enables this, though. It'll run just about as many Wi-Fi cards as your system can support. Even more over the network if you use lightweight systems. So I mentioned, using OpenWRT. In his setup here, each of these is an OpenWRT router with 2 ABGN cards in it, just stacked on top of each other, connected over Ethernet. Eventually, practical limits come into play. If you're doing one system with a whole bunch of network devices plugged into it, after 5 or 10, the kernel can start having a bad time. Some work okay, a lot of them don't. I have seen people try to build 50 or 60 card USB systems, so 60 USB devices plugged into one port. Doesn't work very well. Anyway, if you have network attached stuff, though, we've pushed an Intel i7 server to over 50 cards simultaneously with no problem. It's going to need more RAM and more processor power to handle the packet load the more you try to cover at once. So there you go. Kismet tries to maximize the channel hopping effectiveness in 2 main ways. It will shuffle the channels so that it won't go 1, 2, 3, 4. It will go 1, 4, 8, 2. So it tries to use the overlap to cover as much as it can. Also, if you have more than one card that cover the same set of channels, it will start them offset from each other. So card 1 will start at 1, and card 2 will start at 6, and they'll hop offset from each other so that you get more coverage simultaneously, because you don't want to have 3 cards all on channel 1 and then 3 cards all on channel 4, and that doesn't do you any good. So as you add more cards, all that's handled automatically for you now. So some examples of people who really wanted to see everything that's going on at once. So I mentioned the Wi-Fi cactus. It's 25 of the Wi-Fi Pineapple Tetra from Hack 5. So it's 50 radios, connected to an Intel i7 NUC with 32 gig of RAM. He said that he was seeing at DEF CON, each time he fired it up to 515,000 simultaneous devices. Granted, this was DEF CON. I bet about 10,000 of them were real. He was filling a 2 terabyte SSD every 2 hours with Wi-Fi packets before you offloaded them. So that is, the 50 radios on a camping backpack frame with a lead-acid car battery. I believe he built this, carried it around for a while, and now the dude runs marathons. No joke, he does marathons now. It is not a light invention. For mobile monitoring, this is my own setup where it is... It's just an instant Intel i5 in an industrial case for fanless mode. So it's shoved under the driver's seat of the car and just captures packets for debugging. You can also minimize it down a bit. This is it's a portable rack that I take to conferences, but not this one because I had to fly, which is just a 2U rack with an Intel NUC in it and a bunch of assorted radios all plugged in. So you can get a lot of spectrum coverage. So this has got 5 or 6 different radios hopping across Wi-Fi simultaneously in the size of a 2U tote bag. So it's not too difficult to make portable coverage if you need to do targeted site surveys and whatnot. You can also go extremely portable. So that's an Intel compute stick plugged into a battery pack. And these things have a quad-core Atom processor, 2 gig of RAM, standard Intel stuff, runs Linux, comes with an Intel Wi-Fi card. So that on its own can do Wi-Fi and Bluetooth and Kismet, and it's about $120. They also make a bigger version that's got a M3 processor in it, which is basically the same as the MacBook Air, for slightly more. So how much is too much? This is the Pen 2 guy's setup, where he's got 24 radios plugged into one USB rig for testing. But you can scale for what you need to capture, assuming you have an idea of your facility and what you need to do. So it's got a lot of memory tuning knobs. The memory usage is highly dependent based on what it sees and how many devices there are, because it tries to optimize RAM as much as possible. But some basic rules of thumb. An RPi 3 with a gig of RAM can handle 25 to 30,000 simultaneous devices, and an Intel i5 with 16 gig of RAM can handle about 300,000 devices per session. But that's per session, so that's per running of Kismet. There's no reason you can't use an RPi 3 and reload every every hour and keep your logs on USB. So you can just go back and look through your logs and pick out what you need. There's also device timeout and log timeout options, so you can use it as a long-running IDS sensor without running out of RAM or storage. So when you're building this, we've seen a lot of different antennas connected in. Your antenna choice, if you're looking at Wi-Fi stuff, really matters. You want to pick based on what you're trying to do. Antennas can't add power. They're not amplifiers. They don't give you more. They just take what you have and aim it. They either aim it everywhere or they aim it in one specific direction. You're always going to trade off, somehow you're going to trade off either range or directionality for the different types of antennas. So generally they come in two different shapes. There's omnidirectional, which is, it speaks in all directions, hence omni. They either come out as a sphere or as basically like a donut shape. And then there's directional, which is kind of like the old antennas stuck on your roof for TV, where it's highly directional. It's either, it can be from 180 degrees or down to just a few degrees in one direction, where you get a really good signal, but you only get really good signal at that one very specific area. So all antennas come with these antenna radiation pattern graphs. Learning to read them is going to help you know what your antenna is going to do, and helps you select the right antenna. Fortunately, they're pretty easy to read. So they're usually shown as two graphs, which are elevation and azimuth, or basically X, Y, and Z. So for this antenna, it's basically the same pattern horizontally and vertically. So it's kind of a tube aimed the direction that you're going. So if you look at that same graph in 3D, you'll see that it starts, it comes out as a focused signal. So you can use that to go, okay, I need an antenna to aim from one corner of a building to another corner of a building. So you want a directional antenna that doesn't, shoot sideways or behind you or up and down. So you look for something that is advertised as a directional antenna, and then you can see the antenna graph documents that should come with it and see something like that. And then, they would typically physically look something like that or like that for access points. There's also omnidirectional antennas. So this graph, they decided to label it horizontal and vertical, but still it's X and Y and Z. So over the horizontal, the X and Y, it covers pretty much everywhere in an even pattern out from the access point. And then in the vertical, it's sort of a donut shape. So this kind of antenna would be what you'd find on your access points normally, because when you buy an AP for your house, you want to cover as much of your house as possible. You don't want to cover just one floor or aim your signal at one room. You want to cover everything. So they give you a basic antenna with good coverage like that. So this same one in 3D would look kind of like a donut. Like I said, looks like your standard access point antennas. So a lot of people go, oh, more gain is more better. Unfortunately, it really depends what you're trying to do. Increasing gain decreases coverage because you can't add, it's not adding power, it's just shaping what you already have. You can over-amplify. If you add too much gain, it's like someone screaming in your ear. They're making a whole lot of noise, but you can't really understand what they're saying. So it's possible to have too big an antenna too close to an access point, and you actually will miss packets because they're too loud. Increasing the signal is always going to take it away from somewhere else. So all those cards on Amazon that you see that go, comes with 18 dB omni or 24 dB omni, where do you think that gain comes from? Here's an example of one of those 18 dB omnis. Horizontally, it covers everything, but vertically, it's super squashed down. I've actually seen these where it's so the vertical is so squashed that an antenna on a table here can't see a card on the floor there. Like you get a foot or two of coverage because it's got to come from somewhere. So they add more gain horizontally by losing it vertically. So if you're trying to survey an office, you might miss access points on the floor above and below you completely, or even access points, on a ceiling versus the middle of the room. So you typically want to stick middle of the road, for omnidirectional, for generally monitoring offices and that kind of thing. You'd want, 2 or 5, and they're selling 18 on Amazon. Universal gotchas when you're looking at antennas. Wi-Fi needs antennas built for Wi-Fi. Might seem obvious. You'd be surprised. If you're doing non-Wi-Fi stuff with other radios, you need antennas for the frequency you're talking. You can't take an antenna for CB radio and connect it to a Wi-Fi card and have it work right. This is unfortunate because there's a lot of cheap CB antennas that mount on cars and whatnot, but they won't do what you need. So it's got to be the right frequency. It's got to be 50 ohm impedance. All the cable TV antenna connectors and cables you see out there are 75 ohms. They won't work with Wi-Fi. It's got to be the right connector. Almost all Wi-Fi uses RP SMA. You'll see a lot of stuff for SMA or F or TNC. There's all these other connectors. They won't do what you need. So just check the manufacturer of your card. It'll tell you what type of antenna you need if you're going to buy another antenna. So we can also do more than just Wi-Fi. If you have other types of radios, Kismet can also sniff a bunch of other different things on different frequencies. The Wi-Fi cards can't see them because the chip in the Wi-Fi card is designed to only handle Wi-Fi. Makes it power efficient, makes it really good at Wi-Fi, but it can't do anything else. So to do other things, we have software-defined radio, which has gotten more popularity lately because it's gotten a lot cheaper. So the dedicated radio uses a chip dedicated for whatever it's doing. Cheap to make, really good radio filters that only see the frequency it needs to see, prevents noise interfering with the signal. But it can't see any other protocol. So the SDR uses a generic receiver that can tune to a really wide range of frequencies, and it just passes the data up to the operating system. The upside is it's really flexible and it can see, an infinite, as they like to market, number of protocols. The downside is the software is super, super hard to write, super complex. Because the radio can see lots of other frequencies, it sees everything, which means it sees noise over there interfering with your signal over here. They cost a lot more, and the power consumption is really high, both because the radio chip and the CPU running at 100% to process all that data. There are a few cheap as dirt SDRs. There's one called the RTL SDR. It was designed to receive European terrestrial DVB TV. Someone figured out how to turn it into an SDR. It's not a good SDR, but it's a very, very cheap SDR. This is one of the more expensive ones, and it was $29. You can get them even cheaper. It really is crap. Like, it's a complete piece of junk, but it's so cheap and can do just enough that it justifies the cost. So depending what you're looking for, you can even run multiple of these simultaneously to look at different protocols at once. So we can see things like one of the other common radio bands is 433 megahertz. This is used by things like weather stations, remote control light switches, thermostats, and whatnot. So, if you want to sniff your weather station with Kismet, sure, why not? So it will pull all the stats out of the weather station. You can get temperature and time over, or temperature and humidity and whatnot over time. You can buy cheap little wireless thermometers off Amazon. Can see those just fine, log those. You can monitor buildings, temperature sensors and whatnot with it. There's also ADS-B. Airplanes have a radio beacon that advertises their telemetry and other information that's now required. You guessed it, RTL SDR can see it. So you want to look at airplanes with Kismet? I mean, sure, why not? There's also AMR, which is automatic meter reading. So it's how the power company doesn't have to send a guy up to your house every month now. They're able to read it from the street. RTL SDR can see that. So here's a bunch of power meters in Philly. And so you can watch your power usage or your neighbor's power usage. Bluetooth is a big challenge to sniff, just because of how it works and how the protocol is designed. There's not much hardware out there that can do a good job with it. BTLE, on the other hand, is much easier to find. Kismet will work with onboard cards in Linux to scan for Bluetooth. It won't give you the raw packets yet. I'm working on that still. So it's scanning mode only for right now, but it will look for advertising Bluetooth Classic devices, and it will see most of BTLE stuff, so things like keychain location beacons, Fitbits, all that kind of thing it can find. Would you believe on the flight here there were 480 Bluetooth devices in that plane? There you go. Tile is apparently really popular. That's one of those, put it on your keychain and you lose your keys and you hit a button to look for it and everyone else's phone will look for it and tell you where they last saw it. Zigbee, 802.15.4, is used a lot for industrial control systems. It's also used for some home lighting automation systems and whatnot. Kismet can capture it using a couple of cards. I haven't finished the code to display it correctly yet, but you can capture it and load it into Wireshark. Mice and keyboards. Wireless keyboards and mice often use a thing called the Nordic NRF 2.4 chip, which people have figured out how to sniff. There is a piece of hardware called the Crazy PA. You can buy it on Amazon for $20. Various devices are more or less vulnerable. You can certainly see that they exist. Some of them are completely unencrypted, which means your keyboard and your mouse input is unencrypted. It's a good plan. Some of them allow you to inject packets to them. There are a bunch of attacks going around right now that hijack wireless keyboards and start running commands through them. Kismet can use Crazy PA and detect them. Z-Wave, which is a home automation protocol, you can detect that with the Yardstick 1 radio, which is by the same people as the Ubertooth and the HackRF SDR. That's also super basic right now, but more will be coming. So one of the big things for Kismet to do is detecting attacks going on and what other shenanigans are happening to your network. So there's a thing called a WIDS, which if you're not in Wi-Fi, you probably haven't heard of. So IDS is intrusion detection system. So someone really clever at naming said, oh, WIDS, wireless intrusion detection system. Yeah, great name. I don't know why they came up with that. Kismet can do a bunch of WIDS-like functions. There's also a thing called a WIPS, a wireless intrusion prevention system, which fortunately the marketing seems to have died off on a bit because it's arguable how much prevention you can do against denial of service attacks that just knock your network down. So Kismet focuses on detecting rather than trying to interfere. So Wi-Fi has a shockingly large attack surface. There's denial of service attacks against the Wi-Fi protocol. You can say, I'm your access point, you should disconnect. One packet, it's that simple, and that just disconnects all the users from an access point. You can say, I need the channel for all the time. I need the channel for all the time. And just say that over and over and over again, and no one else can transmit. You can do denial of service against the actual physical RF layer, where you just, have an RF jammer, and then all the Wi-Fi falls down. You think what an RF jammer is an exotic piece of hardware. Analog baby monitor. Those things will just obliterate Wi-Fi near them because they just have a continual transmit across a big chunk of the spectrum of just whatever's in the room. You can do impersonation and spoofing attacks, where you impersonate the access point and either try to trick clients to connect to you without encryption or to connect to you and give you their handshakes or their hashed passwords when they connect. You can try to clone the wireless client and convince the access point to let you in so that you can access the corporate network based off someone who's already authenticated. You can try to use Wi-Fi to steal data from a company by plugging an access point in under a desk somewhere where they don't see it. You can attack the company infrastructure that runs over Wi-Fi. If they use Wi-Fi for industrial control, that's a huge surface to be concerned about. You can also attack the Wi-Fi drivers directly on both access points and clients because the Wi-Fi protocol is really complex and people do it wrong all the time. So being aware of Wi-Fi attacks can be really important. So to deal with this, Kismet has two main mechanisms for detecting alerts, or detecting attacks. There's trend-based alerts, which are based on traffic that isn't inherently wrong, but could be based on changes over time. So an access point advertising that it's unencrypted isn't wrong. But if it previously advertised that it was encrypted, that's bad. Seeing a packet that says all the users should disconnect from this access point isn't inherently wrong. Access points might do that, like the network here would say, if they changed one of the APs here, the AP would tell all the users to get off of it to connect to other APs and then reconfigure itself. That's normal. If you see 500 of those in a second, someone's attacking your network. There's also fingerprint-based sensing where it goes, this packet is malformed in such a way that we know someone is trying to exploit the D-Link drivers, which has happened in the past, as an example. So you can actually see explicit attacks and explicitly malformed packets that perform attacks and detect on those. And you can do user configurable stuff where you can go match the SSID against this regex and tell me every access point that isn't in this list that attempts to advertise it. So you can look for people bringing up spoofs of your network or things like that. So Kismet will automatically learn and fingerprint stuff like encryption settings, the channel, DHCP settings. It'll detect if a client connected to the AP and said, I'm a Windows OS in the DHCP packet, and then immediately also connects and says, I'm a Linux OS, then someone's probably spoofing that client. Or they rebooted, but chances are. You can do regex-based detection, like I said, of the access points. So you can look for your SSID and variations of your SSID. So if someone does your network name but in lowercase to try to trick your users, you could automatically detect that. And there's been a bunch of attacks lately against iPhones, Android, and Windows drivers that can all be fingerprinted and detected. There's a team at Google called Project Zero. And if you want to be terrified and have a good read, just Google up Project Zero and read some of their reports. If Project Zero looks at your product, you're going to have a bad day. The head of Project Zero just found a code execution exploit in Notepad. But they find attacks like they found a way to run arbitrary code on an iPhone from a Wi-Fi packet. So, important things to be aware of. There's also an advanced fingerprint mode in Kismet that's still under active development. But instead of just using the MAC address and the SSID to identify an AP, it will look at all of the other attributes in the beacon packet. So there can be dozens of packets, hundreds of bytes of data in there, some of which changes every packet, some of which doesn't. So we can look into fingerprinting the attributes that don't change, and then if someone attempts to spoof it, they not only have to get the SSID and the MAC address, but they have to get all these other attributes that are often weird enterprise proprietary chunks of data correct in their spoofer as well. It's possible, but nobody does it right now, so it gives us a leg up on that. So, you want to be able to spot the evil twin attacks as much as possible, so whenever someone's cloning your AP. So the more data we have, the more we can look for discrepancies. So we're trying to fingerprint as much of it as we can and roll that into a simpler detection system. Being able to compare things over time and see multiple devices talking simultaneously gives us more of an idea of what's going on. Because when people are making attacks, nobody remembers everything. So Kismet also works on integrating with other tools. Because what good is a tool if it can't talk to other things? If you can't pull that data out and use it, preferably in an automatic fashion, then it's not nearly as helpful. Wireshark's got exporting reports and packets, and T-Shark with scripting that you can pull all sorts of stuff automatically. So Kismet has several APIs to talk to other tools as well. The old Kismet had this weird TCP protocol that was kind of based on IMAP. I think I know of 3 other people besides me who ever wrote anything to talk to it. It was very depressing. The new Kismet is HTTP. It's got a REST-like interface. It outputs JSON. Everything in the world can talk to it. It also has an IPC protocol that can be used as a plugin extension protocol to extend functionality, but you can still get all the data without using that. So everything in the Kismet UI is generated by the REST-like API. So it outputs the standard JSON. The UI is HTML and JavaScript. Any language that can talk HTTP and JSON can talk to Kismet. So, Perl, Python, Ruby, Go, Rust, whatever makes you happy, Node.js. You can use all of that to pull data from the server and create reports on it. It's heavily documented. One of the big failings in the old code was that I didn't write documentation at the time that I wrote the code, and, well, that's never going to happen. So now, documentation, way better. There's Python modules already. So there's a Python module for the database logs, for the web interface, and for several other things. And they're available in pip. It's trivial to query devices and access points and whatnot. It also supports the EKJSON format like T-Shark. So if you're querying 100,000 devices at once, you can parse them incrementally instead of having to receive all of them at once and use all your RAM. It's got automatic windowed device viewing, which is how the UI works, where it only loads the devices that are in the area that you're looking at to save RAM in your browser. So you can use the same thing when you're looking at results. You can see the alerts and messages. You can do streaming PCAP and whatnot. Every field is documented in the code. You can't. The code actually doesn't let you register a field without providing what it is and what it does. So you can actually go and look and see every single JSON field, what type it is, and what it's meant to do. So as you develop against it, you can grab PCAP right over HTTP. So you can. It'll give you a PCAP NG with the original radio tap headers from all the sources Kismet sees. So you can dump that right to a PCAP NG file, or pipe it right into T-Shark and see a live view of that. Also, since it's on HTTP, it also works over proxy. So you can stand it up on an internal network with an Nginx proxy doing SSL and access it from remote. The new log format, Kismet DB log, the old version of Kismet had different logs for GPS and packets and networks, and you had to kind of correlate them all together. The new unified format has packets, system messages, non-packet data from SDRs, the GPS, the device records. Everything Kismet knows about is all wedged into one file. It's actually just SQLite 3 with some normalized data for searching, and then the full records is JSON. So any script that, or any language that can talk SQL and JSON can process the log files now easily. And there's a Kismet DB module in pip already for that, for Python. There's already tools included to convert logs to PCAP, wiggle format, and whatnot. Also, this gives us something Kismet's never had before, which is access to historical data. So Kismet used to, Kismet processes the packet, adds it to the device records, and then logs the packet and forgets it. So being able to go back in time was very difficult. But now that we have a database, we can go back and query data from the past. So there's REST-based APIs that will let you automatically grab PCAP format log files. So you have an IDS alert. Do you want to grab every packet 5 minutes before and after and log it to a PCAP file? You can just do that with one curl command or scripted now. You can grab every packet that's stronger than a certain signal level to see when someone got near you. You can do that automatically now. And it's all queryable through a simple JSON filter that you post to it over HTTP, and you get back your PCAP file. Since also we can generate PCAP on demand, Kismet will now do handshake logging. So if you're looking to test your WPA network, you can automatically capture the WPA handshakes and feed them to Hashcat or Aircrack. It'll also capture the PMK ID, which is the new attack that Aircrack and Hashcat implement. So you'll just see in the UI, it's like, oh, there's the PCAP file, and you can just download it from there, or you can script it. So there's also an IPC API that I mentioned. So interprocess communication, it lets, it's how Kismet packet capture works, but you can also use it to add new plugins without writing C++ code. So you can talk to Kismet over IPC, and it will run your code for you. You can create new web server endpoints with it. So you can create, for example, something that runs Hashcat automatically in the background, or runs other tests when a new user is detected on your network. And it will automatically provide that and provide status on the UI. The UI itself was designed to be extendable. It is, like I said, just JSON and HTML. You can add plugins without writing any C code that extend the UI based on data it already has, or you can replace the whole UI with something else. So El Cantaro has written a full mobile dashboard that's designed to run on iPads and whatnot. So it's all new code that just loads as a plugin. So he's got it all optimized for tablets and whatnot, and you can just extend the UI. You can add different UI frameworks, whatever. Future integration with Wireshark, with the XCAP stuff in Wireshark, we'll be able to directly talk to Kismet and pull packets live into it instead of dumping them to a PCAP file in the interim. So hopefully that'll be up there soon. Also, hopefully we'll be adding the ability to open the Kismet DB packets or log files directly. So, stuff you can do with Kismet, basic war driving or, site survey if you want to be respectable about it, where you're going around a facility and making sure that nobody's brought access points from home, or that all the access points there are configured the way you'd expect them to be. It'll do GPS logging, so you can figure out where the strongest signals are and whatnot, and provide coverage that way. You can do site-wide wireless intrusion with it, all open source. So you can either have multiple remote captures feeding one server, or you can have multiple servers that you talk to and pull all the alerts and events to one location. So there's another project that will be going public soon, which I called Kismet Central, which is meant to collect from any number of Kismet servers. It will find all the networks being advertised, all the devices, and then it will map and create timeline graphs of when access points are active, when clients are active on them, when they've moved between access points and whatnot. And that'll all be open source as well. So it'll monitor, system health, temperature of all the sensors, as well as all the devices connected to them, non-Wi-Fi devices, whatever you have set up. So the ultimate goal will be that you can go, here's the SSIDs I care about, find me everything that matches this regex, then find me every device advertising them, and then you can start spotting, this device shouldn't be here, or this user keeps moving between two devices that are very far apart, something's wrong, etc. Kismet Central is also going to be able to combine log files, so you can upload site survey files to it, and it will combine them in, so you'll be able to spot networks that are misconfigured that way as well as a live view of them. So it's very early days on it, but you can track the different servers and the data sources and whatnot on them, and you can see the timelines of the different devices. So you can see here where my house lost power for a while. And then you can also script against that, so that also outputs JSON. So you can write automatic tools that will just go and say, all right, every 5 minutes tell me all this stuff about my environment, and then script it to your own dashboard or to your own logs or whatever you care about there. And then you can upload the databases to it, and it will track devices in distance and geotag all the devices with the GPS data. So someone had asked at the beginning about getting Kismet. Usually distributions are pretty slow to pick up the new versions. There are packages built automatically both for the releases and for every night's Git code available on the Kismet website itself. Right now it's, the last few Ubuntus, Kali, and Raspbian, because compiling on Raspberry Pi is problematic, so I auto-build them. Yeah, I said that. So yeah, compiling C++ can be challenging if you're going to build it yourself. Kismet's about 3.5 meg when it's compiled. It needs over 2.5 gig of RAM per file for some files to compile, because C++ 11 and templating is very hungry at compile time, but it solves so many problems at runtime that it's still worth doing. So that's why, specifically for the Raspberry Pis and whatnot, I build the packages, because compiling with a gig of RAM on them is very problematic. You can still do it, but I'd recommend if you're just starting out, grab the existing packages. So let's try taunting the demo gods. So before there were a lot of config files you needed to edit. There's still config files that you can tune everything in, but we can also just run it as is. So it's started up. It's telling us to go check it out from the browser. So it started up, but since we haven't added any capture interfaces to it, it can't do anything. So we can go over. And turn on our this is why I said we're taunting the demo gods. Oh, I have a filter turned on, that's why. Okay. Haha, excellent. This is why you don't run the latest code live. There we go. So, there's it running live based on the Intel card that's built into the laptop here. So we can go in and look at, specific access points and see the generic info about them, or we can see the Wi-Fi specific data. So we can, so every field in the UI also has live help now. So, what the hell is MFP? You can click on each one and it will tell you a little bit of information about everything in the display automatically. It will also extract, information about clients connected to it, and then you can jump over and view the details about each client. And it's all configurable for what columns are displayed in what order and coloring of the different columns and whatnot. So we can continue to taunt the demo gods. So I mentioned using XCAP in Wireshark. So here's the start of the XCAP connection for it that will let us automatically connect to Kismet. You can see all the different interfaces, or you can just start a capture. So that's pulling it live out of Kismet into Wireshark. So then if we reconnect to the wireless, the other demo is, I mentioned that you can proxy Kismet via Nginx. So there is my demo system running back in New York, proxied over an Nginx connection. And now I can go like that, and that's live packet capture from my house in New York. So you could also do that cross-campus or cross-facility. There you go. The demo gods have mostly smiled on us. So yeah, coming up next in Kismet is going to be stability and performance improvements. I've got a bunch of ideas for that. Supporting more non-Wi-Fi protocols cleanly, better Bluetooth support and Zigbee support, packages for more distributions as people need them, and remote capture options for OS X and Windows to automate it so that you'll be able to just, take something like this, plug it into Windows, and have it either come up directly into Kismet or directly into Wireshark without any additional setup. And then there's the code in the docs and Twitter, and if there's any questions.
Yeah, I was fascinated by your RF stuff, like the little airplanes and thermostats and things like that. Are those public protocols that you pull in, or are you reversing the protocols after you get packets, or how do you know that?
Most of them are public. There are a set of tools for the RTL SDR that I run and then extract the data from for Kismet. So for the most part, Kismet doesn't do the RF decoding itself. It lets another tool do that and pulls it in. I've been talking with people about optimizing it and making it easier to set up by doing more of it directly. Oh, I'm sorry, the question was protocols like the ADS-B airplane stuff and the thermometers, and if they're public or not, or how you get them. So there's a program called RTL 433, which has 20 or 30 different decoders that people have figured out for weather stations and thermometers and thermostats. And I've seen smoke alarms that use it. I've seen like remote control power strips and whatnot that use it.
I think I remember the concept of that management frame of application being in theory available like 8 to 10 years ago. Can you comment on that? If it's there, or why it's not there, or what's happening in that area?
Yeah, so the question was management frame protection. We heard about it 10 years ago. Where is it now? It's about where it was 10 years ago. There's a little bit here and there. Kismet will detect if it's there or not. So what management frame protection is supposed to do is help reduce the impact of denial of service attacks by making it more difficult to spoof an access point to either disconnect users or to lure them onto a cloned AP. Cisco implemented their own version years ago that wasn't to spec. So there's Cisco MFP, and now there's 11W MFP, which there's a very small number of devices that handle it. There's also WPA3, which just came out, which is supposed to optimize things and solve a lot of these problems, but there's also been a bunch of problems just a bunch of holes poked into it already. So we'll have to see where it goes. And again, not much supports it yet. The problem is that for most things, you've got lots and lots of legacy devices that you can't turn on breaking support for. So, I mean, some of the major vendors don't even have WPA3 support at all yet. So I'd expect it's probably going to be several years before we start seeing it in any sort of prevalence.
There's discussions that when it comes to the illegal authentication with wireless, the only way that you're going to get that full security behind it is with complete stacknet, right? So like WPA3 was just a different implementation, so it's kind of like a revised version of WPA2. And without doing like a complete rewrite, all they did was basically mask small portions of the security vulnerabilities that existed. And it's like you said, they've already punched holes. Like it hasn't even really been released, and they've already punched holes in it and discovered vulnerabilities that are fully breakable. And with regards to like the RTL type stuff, you can just go out there and do like RTL, SDR, open source projects. You're going to come across a whole bunch of listening products you can implement on at home using small, cheap, $20, $30 license.
There's like one of those flight radar sites that's encouraging it. So that
there's
a huge mesh network of. Especially if you're ever traveling in the middle of nowhere, like you're between Salt Lake and Seattle or Portland, you'll see these like things that look like football balls or whatever. They kind of, I don't know, they got like some little hot tower and they're surrounded. That's what they tend to do.
I will say one thing about sniffing various RF stuff, and even in some districts' Wi-Fi, know the laws of your area. The thing I like to tell people when they complain about it a lot online is, there's what's legal and there's what's moral. You might be morally fine to be looking at stuff if you have no intentions of acting on it or commercializing it or something, but it doesn't make it legal. So you need to know what's legal before you open your mouth and talk about what you're doing. The number of people I see who try to submit talks to cons going, I can sniff the pager network and see hospital records. It's like, you can, and the FBI is going to visit you. Shut up. Well, they can't see me sniffing it. They can't, but now you just opened your mouth. So be aware of your legal requirements, especially if you're doing it for work or anything where it's going to be documented and you're going to be using that data for something. You need to know whether or not it's legal. Generally, that comes down to the FCC. In the U.S., it's the FCC.
Wireshark ships with NP cap now? It's supposed to do multimodal meters. Have you looked at that?
I have. If people can, NP cap. It's supposed to. I have not yet found a card that it does on. They're trying. It's difficult. Yeah, I mean, it would be an option once there's a card it works on. None of the ones I have are ones that it does. All right. I think we should probably let them have the room for the next talk then.